In this video, we're going to start Chapter 17, and Chapter 17 is on the principle of linear superposition and interference phenomena. And so we're going to begin by talking about the principle of linear superposition. So let's imagine a slinky that we send a pulse, and we send a pulse from both ends, and these pulses travel together, or excuse me, they travel toward each other, and then the question is, what happens when they meet? Well, if they are both having a positive amplitude or they have the amplitude in the same direction, when they meet, we see an overlap, and when the overlap begins, we get an increase in the amplitude. And so the wave from the right is traveling and it has its own amplitude, and the wave from the left has its own amplitude. And when they meet, those amplitudes add together. Now the key is after they add together, they continue moving left and right. These wave fronts don't change their speed. They continue on, and we see they return to their regular amplitude or their original amplitude and move in opposite directions. This example here is an example of constructive interference where the amplitudes are adding together. However, on the other end, say we have the same pulses, but one is the mirror of the other. And so when they come together and the overlap begins, we see that when they're completely totally overlapped, we see that there's nothing there. It's like the slinky's not even moving, but then the waves continue on and we still see them travel to the respective left and right. This is an example right here. This is an example of destructive interference. The waves are interfering with each other, and when we add the amplitudes together, one's positive, one's negative, then they cancel out. And it's only momentarily that they cancel out. But they do cancel out, and the slinky has no amplitude at that moment there as the wave fronts pass by. And so the principle of linear superposition states that when two or more waves are present simultaneously at the same place, the resultant disturbance is the sum of the disturbances from the individual waves. And so that's where we get this possibility for constructive or destructive interference. We add their amplitudes together because they're two waves that are trying to occupy the same part of space. When two waves always meet condensation to condensation and rarefaction to rarefaction, they are said to be exactly in phase, and they exhibit this constructive interference. A lot of times we try to have this when we have speakers or sound system. We want to have constructive interference because then the two speakers will increase the amplitude, and now we experience a louder noise. Whereas if we have them out of phase, then they will exhibit destructive interference. For instance, if we are a half interval wavelength away from one more than the other, we get this destructive interference. Destructive interference isn't always necessarily bad. We actually use this a lot of times to our advantage. Our phones use this, and noise canceling headphones use this as well. When you have noise canceling headphones on, they actually receive the noise that's coming from the outside. And so we have this noise coming from the outside and some wave fronts coming in. It receives that wave front and it stores the wave front, and it sends the same exact wave front out of phase towards your ear. And so what that does, that wave front cancels with this wave front so that the noise is reduced. And so the outside noise, you almost don't hear it because those headphones are trying to cancel it out. Your cell phones do the exact same thing in that there's a microphone that receives your voice, and there's also a microphone that's receiving the outside noise, and it's trying to send the out of phase signal to reduce that outside noise. If the wave patterns do not shift relative to one another as time passes, the sources are said to be coherent. So for two wave sources vibrating in phase, and so remember, in phase will cause constructive interference, a difference in path lengths that is 0 or an integer number, 1, 2, 3, 4, so on and so forth, of wavelengths leads to constructive interference. So if we have the distance between two speakers or two sources of sound and the difference in path lengths from one source to the other source is some integer of the wavelength, then they're going to be in phase. And so that's going to cause constructive interference. However, if you have the path length that has a difference of a half integer number, such as 1/2, 1.5, 2.5, and so forth, of the wavelengths, this leads to destructive interference. So if we have two speakers, one speaker here, one speaker here, and we look at the interference with these, there are certain points in the room that are called dead spots that will have destructive interference, whereas there's some points in the room that will have constructive interference. And so if we just look at this, we see that when we have crest to crest right here, we have constructive. Trough to trough here, we have constructive as well. Crest to crest here, we have constructive. All right, or you can look at those as compression to compression, rarefaction to rarefaction, either way. But when we have compression to rarefaction, that's where we get the destructive interference in these two spots. And so those are dead spots. And so when setting up a sound system, you want to make sure you limit the dead spots. Now, when we're in a room, one of the things you have to take into account is the fact that the sound is going to bounce off of the walls as well and reflect back. And so that's why in a typical room, there's really going to be no dead spots because sound is bouncing off of all of the walls. However, there are going to be spots that will have a higher amplitude and have better sound. So let's look at an example here. We have two in-phase loudspeakers. We're going to call them A and B, and they're separated by a distance of 3.2 meters, and a listener is stationed at point C, which is 2.4 meters in front of speaker B. Both speakers are playing identical 214 hertz tones, and the speed of sound is 343 in these conditions. So we're around room temperature, regular humidity, all that. So does the listener hear a sound or no sound? So we have to ask ourselves, is there constructive or destructive interference at point C? In order to do this, we need to look at the wavelength and the path difference. So we know that point C is 2.4 meters from B, but how far is it from A? What's this distance here? And so to find that distance, we have to do a little Pythag, and we take the 3.2 squared plus the 2.4 squared, take the square root. And if we want to find the difference between the path from A to C and the path from B to C, we subtract the path from B to C, and we get a path distance of 1.6 meters. And this is the path difference, excuse me. Well, what is the wavelength? In order to find the wavelength, we want to take the speed divided by the frequency, which is 343 divided by 214. That's also 1.6. So these are an integer multiple of each other. And if it's an integer multiple of each other, then we know that there must be constructive interference at this point C. And so constructive interference means we will hear a sound. The last thing we're going to talk about in this video is the idea of diffraction. And diffraction is the bending of a wave around an obstacle or the edges of an opening. And so we look at the idea that if there's no diffraction, a wave front is just going to enter this opening and continue on. And so it really depends upon the size of the opening compared to the wave itself. However, if there is diffraction, what's going to happen as the wave goes through the opening, it starts to spread out as it propagates out of that opening. And so example A here is showing diffraction, whereas example B is showing without diffraction. It's just moving right on through the opening is big enough. And so to determine if this happens or not, we have to look at the ratio of the wavelength and the distance D. So D is the distance that separates our opening, and lambda is our wavelength. And so the angle at which we deviate from the medium here, this angle here, right here, is going to be determined by sine of that angle is the ratio of the lambda, or the wavelength, excuse me, over the slit opening, or the distance between the edge of each edge of the opening. And so looking at this and knowing what you know about trig functions, if the wavelength is bigger than the opening, Well, what does that mean? This is going to be greater than 1. And so if that's greater than 1, sine of an angle can never be greater than 1. And so we're not going to have this angle here, this diffraction angle. However, if the wavelength is smaller than d, and say it's half the size, well then we get sine of theta is equal to 1/2. So we know theta is going to equal 30 degrees. And so we know that the angle here is 30 degrees and the angle here is 30 degrees. And so we're going to open up in a total of a 60-degree angle out of the opening if the wavelength is half of the opening distance.